courses.
The full screen is not shown. Cool.
Good. Awesome. Okay, so for our last talk of the day, we have Mark Sellke, who's going to be talking about optimizing.
Okay, thanks everyone for coming, and thanks to the organizers for the invitation, the nice workshop. So I'll tell you about tight algorithmic thresholds for optimizing mean field spin glass Hamiltonians, and this is joined with Bryce, who just spoke. Okay, so what I'll do today is as follows. I'll set up the problem, tell you what these functions we're trying to optimize are. Then I'll fill you in on various background material. I'll tell you about our new result, which is a tight characterization of the best value you can achieve with a certain class of efficient algorithms. And then I'll tell you about some of the key ideas involving ultrametricity and a branching version of the overlap gap property. Okay, so here's the model in one equation. We're going to construct a random function hn from Rn to R. It's going to be a random polynomial of degree capital K. And the coefficients will basically be IID standard Gaussians. It's just that there's some scaling. So there's some scaling, which is a power of n, which just ensures that every degree contributes on the same order. And there's some constants gamma, which are just differing depending on the degree. An equivalent description is that we can put all these gamma constants together into a one variable polynomial xi. And then hn is just a centered Gaussian process with covariance given by taking a normalized inner product and applying xi. So xi is kind of a nice way to encapsulate all of these coefficients into one nice object. We're going to look at two input sets today and kind of I'll treat them in parallel. There's the Ising case where we look at inputs on the cube, and there's a spherical case where we look at inputs on the sphere. Okay, let me tell you a little bit about the motivations and history. So the first model like this is, I think, the SK model, which is a quadratic Hamiltonian. And it was introduced to study various types of magnetic alloys. And what happens here is that the magnetic interaction between particles is kind of depending in a complicated way on the distance. So we just think of it as an Ising model with random couplings. Okay, and then if we want to make our lives a little bit easier, we forget that we're in a 3D space and we just take a mean field version of the problem. So we make all of the couplings IID. From this point, taking higher degree extensions and spherical inputs are mathematically natural just to give ourselves kind of a bigger sandbox. These models also arise in various other ways. You can reach them as high degree limits of things like max cut and max set. They're also just a rich source of random non-convex functions, and they're related to some neural network models. Okay, now probably the most celebrated fact about these mean field spin glasses is the Parisi formula, which was proved by Talleyrand, and there are various other results that I've listed here. In a nutshell, what the result says is that in both the cube and the spherical case, if you look at the maximum value of this Hamiltonian, appropriately normalized and in the large n limit, it'll have some limiting value. I'll call this opt. And this limiting value is given by some sort of explicit minimization problem over the space of increasing functions on the interval 0, 1. So there's a different Parisi functional in the Ising and the spherical case, and I won't actually write it down, but there's some minimization problem over increasing functions. So the main question I'm going to try to address today is, what can we do with efficient algorithms? Can we come up with efficient algorithms to reach this optimal value? And if not, what kind of value can we reach efficiently? Does this problem make sense? Great. Probably many of us have heard a couple talks about this type of thing before. Okay, so let me quickly say something about the landscape. So if we have a function that's close to convex, maybe we can just do gradient descent, but this isn't really what happens. So these functions, if you look at them on the sphere, they can have a huge number of near optimal local maxima, which sounds like maybe it's good, but they have even more places we get stuck that aren't so good. So we probably can't just use gradient descent. I also want to mention that if you have a worst case problem instance like this, you can't even get a constant approximation factor. So we're going to need to use the randomness, and we probably can't use gradient descent. But it turns out that as far as computational complexity goes, we don't have to look too much further than gradient descent. So there have been several recent papers on this, starting with Subag, and then Andrea figured out how to do it for the cube. And in a nutshell, the result is that we can achieve a smaller value called alg, which is given by the same minimization problem, but over a larger set of functions. So previously, for the true maximum value, we have to minimize over all increasing functions. But this algorithmic value is given by minimizing over like kind of all functions. So they don't have to be increasing anymore. In these case, we have to assume that a minimizer to this variational problem exists. Okay, approximate message passing is really efficient. It only uses a constant number of gradient queries, and it's great for a lot of statistical problems, as we've heard about. A very, very brief summary of this type of algorithm is that there's a stochastic differential equation related to this Parisi formula, and we're going to simulate an associated stochastic differential equation using AMP. And we actually showed that if you use an AMP algorithm with this very specific setup, you cannot do better than this alg value. Roughly speaking, when alg equals op, this corresponds to a no overlap gap. On the other hand, when there is an overlap gap, which actually is essentially just on the complement of when AMP works, you can show that no sufficiently stable algorithm can achieve opt. These results hold basically in general, except that you need to assume that these odd coefficients are 0. So there's no odd degree terms except maybe the linear term. Okay, so stable algorithms include a lot of things. They include constant number of gradient descent or AMP iterations, Langevin dynamics, low degree polynomials, many things. And the proof is based on this overlap gap property that Bryce just talked about. It's a family of topological hardness criteria. There have been many papers on this kind of thing. Let me show you another sort of cartoon of the overlap gap property. So we're going to consider an interpolation path. In this case, we're just going to take two independent Hamiltonians, HN0 and HN1, and we're going to interpolate between them so that everyone along this path has the same marginal. And the idea here is that morally, the algorithm gives us a continuous path, and there's some intermediate distance, QOGP, that we have to cross by continuity. And the overlap gap property lets us say that if we have 2 points at this intermediate distance, QOGP, then they can't both be near optimal. And that's how you can show that stable algorithms can't reach opt. Okay. So the new result I want to tell you about today is kind of similar statement, except we can get all the way down to alg. So we can show that no algorithm satisfying a certain overlap concentration property is able to get any better than alg. This is again for even models, and it doesn't include quite all of the algorithms that Gamarnik, Dragunov, and Wen were able to rule out, but it includes AMP and gradient descent and things that look like that. Moreover, it holds in a strong sense. So for all of these algorithms we can handle, we can actually rule out anything better than an exponentially small in n probability of getting better than alg. And to give you some idea, this is the same up to the constant in the exponent as just ignoring the input entirely and just guessing a random point. The proof is going to rely on a new branching version of the overlap gap property. And right at the end, as I'll try to explain a little bit more, we can show that in spherical models, we kind of actually need to use this branching overlap gap property, and any kind of simple OGP is not able to get all the way down to alg. Okay, so the core idea behind what we do is based around ultrametricity. So let me remind you what an ultrametric space is. An ultrametric is a stronger type of metric space that has to satisfy this ultrametric triangle inequality. Another way to think of it is that it's a hierarchical clustering, or you can just take a tree and look at the corresponding graph metric on the leaves. And it's known with some technical caveats that I won't get into that if you look at the positive temperature version of this problem, so you look at the Gibbs measure proportional to e to the beta h, then it's sort of supported on an ultrametric space. So this is some deep stuff that has guided the study of these models since the beginning, and it's it kind of suggests that ultrametricity should be related to these models, even for algorithms maybe. And here's a way that algorithms for these models are related to ultrametricity. You can build more outputs than just one with these algorithms. So the AMP algorithms for this problem, roughly speaking, explore by taking many small steps because they're simulating a stochastic differential equation. And you can define a branching version of it that kind of re-randomizes things a couple times and creates a bunch of different outputs. If you do this, you can construct a bunch of outputs. And in fact, for any fixed size ultrametric space X, you can output a bunch of points whose metric structure is the same as X. And each of them attain the same energy value alg. So if we can do this with algorithms, then this suggests maybe we can use a really strong version of the overlap gap property that kind of matches this ability. So in the classic OGP, we're ruling out pairs of solutions. In something I'll just call a one-layer OGP, we can rule out tuples of more than 2 points where all the distances are about the same. There's also something you might call a ladder OGP with some kind of multi-distance thing like what Bryce was talking about. In a branching OGP, we're going to be ruling out configurations that approximate an arbitrarily complicated ultrametric space.
I suggest that we call it deep OGP.
Deep OGP.
Let's replace our funding.
Which is also pronounced dog pee.
Okay, so to be clear, a very complicated ultrametric space is nothing mysterious. It's just a tree that's kind of branching constantly at all levels. So it's a tree that branches maybe every depth delta or something. But as you can see, it's going to be more complicated than these other types of configurations. Okay, so the first question that may come to mind is like, how would we get to hardness from here? So in versions of the OGP that are like these previous setups, you can imagine some continuous path where you stop at the right points, like what Bryce was explaining in his talk. And if you stop at the right points, you get a configuration like this. So we're going to do something different, and it's why we need this notion of overlap concentration. So we're going to say an algorithm is overlap concentrated if the following occurs. So we fix T, and we take 2 inputs that are kind of correlated by an amount T along this interpolation path. So we're taking Gaussian coefficients for our random polynomial, but they're correlated on the 2 problem instances. And the algorithm is going to be overlap concentrated if the distance between the outputs tightly concentrates around some function of T. And this concentration quality should be uniform over the value of T. So what does the picture look like? It looks like we look at several different interpolation paths, I'll just say from the same point. And previously, we said that by continuity, they have to reach this moat somewhere. And overlap concentration is going to say that they reach the moat at the same time. So at the same value of T, they're reaching this moat. This property is a bit stronger than stability, but if the algorithm has some suitable type of Lipschitz dependence on Hn, then it holds automatically by just concentration of measure. And this is how you can show that things like gradient descent and AMP satisfy this property. But we don't know how to show it for low degree polynomials. We're not sure if it's true even with some extra types of nice assumptions. Okay, so what can we do with an overlap concentrated algorithm? So the first step is that we're going to take some arbitrary ultrametric space X, and we're going to create some correlated Hamiltonians, one for each point in X. They're going to be correlated in such a way so that when I have 2 points, X1 and X2, that are close, according to this ultrametric, then these Hamiltonians will be more correlated together. So you can generate them by taking like a Brownian motions on a tree to generate the Gaussians. And overlap concentration is going to say that if I apply my algorithm, then all of the distances will transform deterministically. And this means that I'll get a new ultrametric space just by applying this transformation function chi to every distance. Chi you can show as continuous. So that means that we can get any ultrametric we want on the right-hand side as a structure of outputs for the algorithm. Okay, so what this means is that if we have an overlap concentrated algorithm that achieves a value alg plus epsilon, then by choosing X on the left-hand side appropriately, we can get a configuration of algorithmic output sigma that approximate whatever ultrametric we want. And each of these points has a large value of Hn. Is this okay? Okay, great. So let me just say a little bit about how we can rule out such a configuration, and then I'll be finished. So we're going to take this forbidden structure chi of X to be a KRE tree that branches at every multiple of delta. So kind of a continuously branching random tree. In fact, these are sort of universal for finite ultrametrics. So if I have any finite ultrametric with an appropriate diameter bound, I can approximately embed it into an appropriately fine-grained tree like this. So we're using the full strength of the ultrametricity. Okay, there's an upper bound proof for the Parisi formula based on some interpolation, some fancy Ruel cascades. And somehow it generalizes to Richter settings like this one. And what we can do is we can uniformly over all configurations with this type of metric structure. We can control the average value of Hn over these points. So it's just like bounding the maximum value, but overall configurations with this structure, and we just average the energy over the point set.
So their X is fixed, capital X is fixed.
Yeah, we fix the ultrametric structure. Yeah, we take n to infinity. So just like in the classical Parisi formula, somehow if I give you any increasing function, it can be plugged into this type of upper bound scheme, and you get an upper bound at the end. So you can express this as a multi-dimensional generalization of these Parisi functionals. Okay, and it turns out that if you work at it, you can transform this multi-dimensional Parisi functional back into some stuff in terms of one-dimensional Parisi functional. So we're back in like, we found this ordinary Parisi functional again, but the increasing function we started with actually transforms. We don't get the same increasing function at the end. We get something that's no longer increasing. So this is how we're able to get to non-monotone functions, which went into defining alg. Yeah.
What is the paper where this calculation of the theorem is done?
I mean, so I think it should be in Holograms work.
What was the motivation for looking at different X, different Hamiltonians? Because the HX are different Hamiltonians, right?
Oh yeah, okay. So for that, it might not be in Holograms work. Like I guess it's called like vector spin glasses. I think that keyword should include it. I mean, somehow it's like, if the same proof technique works, maybe someone will work out how it works. I'm not sure exactly what the first place to consider slightly different multi-integers.
I think the vector Hamiltonians literature only considers different configurations on the same. But the technique shows.
So you redid the calculation for different Hamiltonians.
Just to understand.
Yeah.
But just the upper bound, right?
Yeah, just the upper bound. Yeah, but yeah, so you also have to redo everything carefully because like you can't assume chi is like independent of n. You can't assume chi is a fixed function. It can depend on n. Its modulus of continuity can blow up with n. So you have to kind of do everything pretty explicitly. Yeah. Other questions about this? Okay, I'll just finish up. So somehow this increasing function that we can plug in to get a bound turns into a no longer increasing function. Let me show you what actually happens. So it's very similar to the original function. The ratio is piecewise constant, but basically the transformed function you get out that you plug into the ordinary Parisi functional shrinks at every time this tree branches. So it shrinks at every multiple of delta because we looked at an ultrametric tree that branches at every multiple of delta. And it's now just a matter of observing that if I have a function that's like increasing, but I can decrease it every multiple of delta, then I can take any reasonable function I want and build an approximation to it just by decreasing it kind of the right amount every time. So that's how you get an upper bound of alg plus epsilon. You approximate an arbitrary non-increasing function. So there's no need to assume that a minimizer exists here. You just approximate anything. If we compare this to what happens with the classic OGP forbidden structure, you have a tree that only branches once. What this means is you get a function at the end that only can decrease once. So you break out of like increasing function land, which is why you can get below opt, but you can't approximate a general function with a function that can only decrease once. This limitation is kind of fundamental. What we can show is that at least in a spherical model, if you want to rule out alg plus epsilon using a forbidden ultrametric tree, then these trees have to contain full binary subtrees of size that diverges as you send epsilon to 0. So you can take an ultrametric structure that's really large, but if the largest binary subtree, largest full binary subtree in it has bounded size, this is some notion of parametrizing the complexity, then you won't be able to reach all the way down to alg. Okay, and if you have a full binary tree of unbounded size, you basically have this branching construction. So that's the sense in which I mean that this is necessary. Okay, let me just conclude now. We looked at the problem of optimizing a mean field spin glass Hamiltonian, and we showed that this alg value is the best asymptotic value achievable by a certain class of algorithms that we're calling overlap concentration. These algorithms include constant number of iterations of gradient descent in AMP, and the proof uses a branching version of the overlap gap property based on general ultrametric trees, which is in some sense necessary. A natural open direction I'm very excited about is to see if this kind of branching OGP can identify the exact algorithmic threshold for more general problems, because this connection seems like it could just be very general. Thanks. Let me know if you have any more questions. Yeah, Sam.
How much hope is there to bring other algorithms into the fold of what would be ruled out by this kind of this kind of concentration OGP?
Yeah, that's a very good question. That's also a great direction. So yeah, I'm not sure like if it's possible to show that like low degree polynomials satisfy this property, maybe if you make another nice assumption or two, or if like this proof technique can be relaxed a little bit so that you don't need overlap concentration exactly. Yeah, I'm not sure. There are also just algorithms where it's like if you look at something like Glauber dynamics, it seems like maybe it's overlap concentrated, but it's not easy to show that it is. So that's also something that could be done. Yeah. Yeah.
So that's something from earlier. Towards the beginning, you made this remark that if you run this AMP together with branching, you reach a bunch of points. Those points, the metric structure on them approximates in sometimes the ultrametric tree. So then also it seems in some sense to approximate the Gibbs measure itself. And yet sampling from the Gibbs measure at low temperature for let's say SK model should be hard, right? So there is something broken in that.
So I think like what you can think happens is like you have a big ultrametric tree, right? And the Gibbs measure is going to like Okay, so like maybe these are all the points that have value up minus epsilon. Okay, there's a lot of them. But if you look at the Gibbs measure, the small energy differences will matter enough so that the support is really on a pretty small amount of this tree. I think that's kind of the cartoon I have in my head.
So maybe you kind of get, some kind of, it's like the sense in which something is a good approximation of the Gibbs measure or not. Like to be really a good approximation, you would have to have a lot of points like fine granularity kind of that.
Yeah. This is all just like a first order.
Approximations are also on the linear scale, so only approximate multiple.